Well, and the last ecological model that I would like to explain is the predator-prey model. Right? So here we have the ecological scenario with two species. One of them preys on the other one. So this is a very, very simple model. Right? So notice that uh, here there is no negative x squared term and there is no negative y squared term. Right? So which means that we do not try to do the logistic growth. Right? So rather than that, so if you look at this system of equations, so for x, right, so x is the predator, right? So what it tells us is that without prey, which means if y were 0, then x would die out because its intrinsic growth rate is negative, right? So imagine that uh, there is no this term. So if y is 0, then it's just x prime is minus 0.05x. Right? So which means that on its own it would die out. So what sustains it is this positive term. So which tells us that whenever x and y meet, their encounter is beneficial for x. So in other words, it actually means that it preys x preys on y. Well, and then, well, of course, since the intrinsic growth rate is negative for x, we don't really need to restrict its growth by subtracting any quadratic term in x. Now, the equation for y, so y is the prey here. It looks like this. This is the equation for the prey. So notice that if in the absence of the predator, we would not have this term. So if x is 0, so then on its own, y would experience unbounded growth. Of course, it is not a realistic scenario, but it's just it's a very simplistic model. So we do not introduce the quadratic term for y square because what limits the growth of y is the presence of x. Right? So the negative term here with xy tells us that whenever x and y meet, so any encounter between x and y is bad for y. So which essentially means that y is eaten by x. So that's the logic of the model. Well, let me just think. Let's just speculate a little bit. So what's going to happen? Let's suppose that initially there are very few wolves and very few moose, right? So, and then what's going to happen is that this the rate at which wolves eat moose is small because xy is small. So then y is going to experience exponential growth. Then when it's growing, so if y is growing, then x starts to grow, right? Because of the positive term with xy. And then x starts to grow. But then when there is too much x, y is going to start decreasing. But then x is going to still increase. But then when there is too few x, there's when wolves have eaten too many moose, then the population of moose is going to decrease, and then it's not going to be sufficient food for wolves, and then the population of wolves is going to decrease too, and so on. So, in other words, from the kind of the naive understanding of the model, what we are going to see is cyclic behavior when the population of moose grows, then decreases, then grows, then decreases, and the population of wolves also grows, decreases, grows, and decreases with a small delay after the moose. And it actually happens. It's just that let us see what's going on here. Right? So let's find equilibrium solutions. Now, from the first equation, we see that either x is 0 or y is 125. And then from the second equation, either y is 0 or x is 40. And thus we get two critical points, 0, 0 and 40, 125. So here is the Jacobian matrix. So now let us analyze the type of the critical point from the Jacobian matrix. So I suggest that you try to pause the lecture now and try to answer this question by your own. How to find the types of critical points without actually substituting, without much calculation. So let me explain now. So let's do 0, 0. 0, 0 is easy, because if it is 0, 0, then if x is 0 and y is 0, it just means that all these terms are gone. And the remaining part is a diagonal matrix with a negative number and the positive number on the main diagonal. So one of the eigenvalues is negative, the other one is positive, so it is a saddle point. So let me do 40, 125. So with 40, 125, so notice that the equation that gave us 125 is this equation, and if you did cancel by x, then the remaining thing is exactly this. So which means that if you substitute y1 equal to 125 into this Jacobian matrix, then this term is going to disappear. And by the same logic, this term is going to disappear. So the Jacobian matrix looks like this: 0 here, 0 here, a positive number here, and a negative number here. But then it means that it has to be a center point. Correct? And because the trace is 0, determinant is positive, and discriminant of the characteristic equation is negative. And it is actually true. So we see that what we saw is that the linearized system has a center point. But it turns out that the original nonlinear system also has a center point. All right, so here we have two solutions and trajectories. So this is the phase plane. So trajectories, they're cycles that go around the equilibrium. And this is what is x? So here this is y, and this is x, and this is t. And these are solutions. So we see that indeed, as we kind of naively expected, the populations of predator and prey, they exhibit these cyclic oscillations. So now let us confirm that. So the important point is that if the linearized system has a center, the original nonlinear system may not have a center. Right? So let us, in order to confirm it, we have to calculate trajectories of the nonlinear system. Right? So to calculate trajectories, we divide y prime by x prime, and then we get a differential equation on x and y without t. So notice that this is a separable equation, and then we can solve it. So here it is a separable equation. It's a very simple one. So here we get integral of 1 minus 125 over y dy equals integral of 500 over x minus 20.5 dx. So it is a straightforward integration. So we just integrate and solve it. So notice that since we are looking for solutions where x is positive and y is positive, the antiderivative of 1 over y is just ln y. You don't need the absolute value here. So here is the answer. So in other words, what we get is that the equation of trajectory is this. So trajectories are curves defined by this equation for different values of the constant. Well, solving this is impossible in the sense that you cannot really express y as a function of x or x as a function of y, but you can still plot it in Desmos. So here is the plot. And we see that, yeah, they do indeed like closed curves. I deliberately did not prove that they are actually closed curves rigorously, so it's just a plot. So it is again a little challenge for you to prove that um, these are closed curves. So if you solve it, please share your solutions as comments to this YouTube video. Well, of course, it's clear that well, the choice of specific constants is not important. So simplest predator-prey model is just like this, where x prime is minus epsilon 1 plus. So this is the predator, and y is the prey. So we can see it from the fact that well, encounter between x and y is good for x and bad for y. So the xy term in the predator equation is positive, in the prey equation is negative. So that there is just one equilibrium, and this equilibrium is going to be a center point for both the linearized system and the original nonlinear system. So trajectories are going to be closed loops encircling this equilibrium, and which means that solutions x of t and y of t are some periodic functions. Let me just note again that it is impossible to find explicit closed forms for x of t and y of t. So it is possible to plot them on a computer, and it is possible to prove that they are actually periodic functions, but it's not possible to actually calculate them. I am pretty sure that it is also possible to find a period of oscillation, but I don't remember how. So we're not going to do it. Right? So now let us modify it a little bit. So a reasonable modification is to assume that if you take the prey, then if left to its own, the prey cannot grow. Its population cannot grow indefinitely. So there should be some term that limits the population growth of the prey in the absence of the predator. And this is what we did here. So we introduced a quadratic term. So let us see what changes. Are we still going to experience periodic oscillations or not? Well, so x is the predator, y is the prey, right? So the purpose of introducing this is to limit the intrinsic growth of the prey population. So in this case, the intrinsic carrying capacity of the prey population is 200. Well, and then if we look at the phase portrait, we see something different. So now there exists there still is a critical point with both positive populations, but now it's not a center point. Rather, it is something asymptotically stable. So all trajectories converge to that point. So is it a node or is it a spiral point? From the looks of it, when the population going to stabilize, so they do not look like decaying oscillations. So it is probably a node. So let us confirm it analytically. So first we verify that it is indeed a critical point. Then we compute the Jacobian matrix, and then Jacobian matrix at the given critical point is this. While its determinant is positive, its trace is negative, and the discriminant of the characteristic polynomial happens to be positive, which means eigenvalues are real. So the product of the eigenvalues is positive, the sum is negative, which means both of them have to be negative. So it is a nodal sink. Since the linearized system has a nodal sink at the critical point, it means that the original nonlinear system also has a nodal sink. Well, and finally, a little problem for you is that is it possible that you change this logistic term so that the predator-prey system has a spiral sink instead of a nodal sink? Or is it possible that the critical point becomes unstable, or there is no critical point at all?